Good day, good evening, Year 12 Physics students. Welcome to this lesson on reflection of light, part 2. The focus of this session, this lesson, will be on spherical mirrors. So we'll cover the features of spherical mirrors. We'll talk about the terminology associated with spherical mirrors. So, things like focal points, centers of curvature, the principal axis, and we'll talk about the two main types of reflecting, converging and diverging. Which then leads us nicely into concave mirrors versus convex, mirror formula, magnification, so a bit of mathematics associated with it as well. Okay, so let's start just by talking about spherical mirrors. Okay, so you can see I've got a couple of diagrams here, so don't let this red section here distract you. It's just there to show you that this thing here, which is our mirror, our concave mirror, is just a section of a sphere, or a circle. Okay, so the curvature is consistent with a circle. So if we imagine, I'll just take that sort of out of the picture here because I don't want it to distract. Okay, but you can imagine the circle. Okay, so what do we have? We have a concave mirror here, right? So it reflects on the inside, and we have a convex mirror here that reflects on the outside. Okay, so let's start with the concave mirror. We call this a converging mirror, and you'll see why in a second. The principal axis is the axis that runs through the center of the sphere or the circle. We call it the center of curvature. So coming back up here, the center of curvature. So that's essentially the center of the sphere. And we have this thing here, it's called F, it's a focal point or the focus. And it is halfway between the center of curvature and the actual mirror. So we can just write that little formula here, can't we? We can say that C is equal to 2F. Okay, now I'm using lowercase f here because I'll use uppercase F to denote the actual focal point, but I'll use lowercase f to represent the distance. Okay, so we'll put that in a second. So basically the distance from the focal point to the mirror is f, and we can say the distance from the center of curvature to the mirror is c. Okay, so we can say c is distance to center, and little f is distance to focus from the mirror. Okay. Rightio. So we have a principal axis running through the center of curvature to the mirror. Over here, similar thing, we have a principal axis running through the center of curvature. The difference between a concave and a convex, you'll see straight away, is that the center of curvature and the focal point are on the back side of the mirror, the virtual side of the mirror. Here, they're on the real side of the mirror, okay, the reflecting side. Just to see why one is converging, one is diverging, why one is converging and why one is diverging, let's just put a few rays in. So we looked at ray diagrams in the last lesson. So what if I have a parallel ray, so a ray that's running parallel to the principal axis, right? So coming in and hitting the mirror. Now by law of reflection, we know that angle of incidence equals angle of reflection, and what we'll find is that this ray will reflect back through the focal point. Okay, now there's a reason why it's called a focal point, and you'll see why. If I put in another parallel ray, say one up here, we'd find the same thing. Okay, it would reflect through the focal point. Okay, so something like this. Yep, something like this. But I don't want to put in a bunch of rays because I'll just focus on, say, a set of rays emanating from one place. So we could say there's some sort of, let's do this. Let's say there's an object here. Okay, this is my object. Okay, so I've got a ray coming from the top of the object, running parallel to the principal axis, reflecting through the focus. Okay, I'll write this down in a second. Another ray we could put in there would be one that goes from the top of the object through the focal point, okay, and then reflecting parallel. Okay, so that should be easy to remember. Okay, so the parallel ray reflects through the focus, and the ray coming through the focus reflects parallel. And this can all be proved or verified, geometrically, by considering that angle of incidence equals angle of reflection. And so if we put a normal in at this point here, normal to the tangent that is, we can see that those angles I and R will be equal to each other. Now, that's pretty much all you need, because what we can see here is we've got two reflecting rays that are intersecting, okay, and they're intersecting at a point, and it turns out that that point, now, it's not where I want it to be, by the way, because the center of curvature is kind of in the way. So I'll let that dry for a second. But what we find is our object here, this is the object, will form an image in this concave mirror somewhere about here. Now I know that was a bit impatient of me, but I'm just going to force that little arrowhead in here. So that will be my image. That will be my image. Okay. Now the center of curvature hasn't disappeared, so I'll just put it here. That's C. Okay. Now I had to move the C because the image, if we have the object outside of C, the image will be inside of C, and that's one of the cases that we'll get to. So a couple of things here. Okay. A couple of things about this. It's a concave converging mirror. Okay. What we see with this particular image is it's a real image. So if we look at the characteristics of the image, we say it's a real image. We say it's inverted because it's upside down. And the other thing is we'll see that it's reduced in size. It's actually smaller. Okay, so we talked about plane mirrors. We said that the distance to the image is always equal to the distance to the object. This is not true here. We can clearly see that the distance from the object to the mirror is greater than the distance from the image to the mirror. Okay, so, but we also find that the height of the image is shorter than the height of the object. In a plane mirror, the height of the image is always equal to the height of the object. Okay, so, but look, this is not the only case. Okay, there are cases where, with a concave mirror, there are cases where the image is not real, it's virtual. There are others where it's magnified. So we'll get to that. Okay, so the main thing to sort of take away here is that we can put in two rays, right? So one parallel reflecting through the focus, one through the focus reflecting parallel. Where they intersect, that's going to be where the image is. We could do a third ray. Now, I don't tend to do the third ray, but you could do the third ray, and that third ray would be coming from the top of the object through the center of curvature, hitting where the mirror is, if the mirror's there, pretend it's there, and then reflecting back through the center of curvature. Okay, so we find that, if a ray, let's say we've got a ray running along the principal axis here through the center of curvature, through the focus, when it hits the mirror here, it's hitting on the normal line, basically in line with the normal line. So it will reflect back along that line. Okay, so that should make sense. So we can put in a third ray. And in fact, you can put in infinite rays, really. It doesn't matter. I could throw a ray up through here. It would reflect somewhere, not necessarily through the focus because it's not parallel, but I would find that the reflected ray would still go through that point. So there you go. All right, so that's an example of a concave mirror where the rays converge. Okay, so converging meaning they head in towards the focal point. That's what converging means. Let's come over here to the convex one now. So if I do a similar thing, if I put an object here, right, call that my object, and I throw a ray that's parallel, it will reflect off at some angle. It will reflect off at some angle as if it's coming from the focus. So the focal point. So if we put in an imaginary line here, imaginary ray, then we'd have a ray sort of heading off in that direction. So it's kind of in line with what happens over here. A parallel ray will reflect through the focus. So here we have a parallel ray reflecting as if it came from the focus. Okay. the other thing we can do is we can say, well, let's have a ray that, say, is heading towards the mirror, right, as if it would go through the mirror and then through the focal point. Okay, so we've got that ray there. Now that one will reflect parallel. Okay, so that will be that ray. Now what we find here is these two rays, it's the incoming, so these two reflected rays don't meet on this side of the mirror. But if we go back through here, we find, yes, they will meet virtually behind the mirror. And so we have an image that forms behind the mirror. And this is our virtual image, okay? So this is the image. And in this case, we have a virtual image, which by the way is reduced, but is upright. Okay, so three characteristics of an image. What is the type of image that it is? So we saw over here, we had a real image. Here we've got a virtual image. So it's which side of the mirror is it on? And you might recall that a real image is an image that can be projected onto a screen. Okay, so here we could, if we had a screen sitting right there, we'd see the image. Virtual image you can't. Okay, you can't see that on a screen, but you can see it in the mirror. Here we had an inverted, so it was upside down. Here it was upright. Here it was reduced. Here it was reduced. Okay, so now with the convex mirror, it's called a diverging mirror, and we can see that because the rays diverge off away from each other. Here they converge in towards each other. Now with this one, there's only really one case, okay, because the object is always going to be on this side of the mirror, and its position relative to the focal point and the center of curvature never really changes. The distances change, but in terms of where it's positioned, it's always this side of the mirror. However, over here, if we look at our concave mirrors, we find that the object can be outside of C, it can be inside of C. Inside of C can be between C and F, or it could even be inside of F. We can even place our object at the center of curvature. We could even try to place it at the focus. Something weird happens there. We'll get to that. So just to summarize this little bit in here, concave mirrors, there are many cases of types of images that are formed. Convex, there's only really one, okay? But obviously the position of the image and the size will vary, but it's always going to be virtual, it's always going to be upright. Okay, so I guess I've really just started that discussion about concave versus convex. So let's just have a really quick look at concave mirrors in terms of the cases that I was trying to outline here. So now I have a handout, which is going to be a lot neater looking than what I'm about to create here. So you refer to that handout. The textbook also has some good information about all the cases of images that are formed in concave mirrors. But here I go. So I'm just going to draw up a bunch of concave mirrors. Now I think we can talk about maybe 4, maybe 5 cases. Okay, so I'll just start with 4. Okay, so and we'll just put our principal axis in each case. Okay, so something like this. So we'll call this case 1. This can be case 2, case 3, case 4, and we're looking at images formed, okay, in a concave mirror. So let's place a focal point and a center of curvature in each of these. So I used to do these diagrams using rulers and compasses, and you can get it fairly accurate, but this will do. Okay, so that's C, that's F, that's C, that's F, C, F, C, F, and we can talk about C as being the distance C to here being twice the distance from F to here. Okay, so our 4 cases. 4 cases. We'll start with an object here, outside of C. Then we'll look at an object at C. Then we'll look at an object between C and F. And then we'll look at an object inside of F. So I've really I haven't done a good job on this one. Just fix that up a bit. So that's probably still not good. Okay, we'll get that right. Okay, so they're the objects. So that's, I'll just say OBJ for object, OBJ for object, OBJ for object, J for object. So that's going to be the center of curvature on this one. Okay, so we can say, you know, we can say outside of C, at C, between C and F. So between C and F, and here we can say inside of F. Okay, and we're just talking really about the position of the object in relation to the mirror. Okay, so what we find is this object will have an image that is down here. Okay, this one here will have an image here, this one here will have an image here, and this one will have no image. This one has an image over here somewhere. Now it's actually, this is a tricky one to go over, but here's the image here. So let me just write image, 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 image. Now I won't do the ray diagrams. I mean, I could, but it'll look really messy. But just, if you do the ray diagrams as I outlined back down here, you'll be able to produce these images just like I've done here. So the thing to take away here is that this image is real, right? This image is real, it's inverted, and it's reduced. Okay, and we always find when it's outside of C that you'll get a smaller image. Okay, as you move the object in, all right, and so we get to C, we find that it's still real, it's still inverted, but we find it's neither reduced or magnified. We have the height of the image. The height of the image is equal to the height of the object. Okay, so that's the only case where that happens, right? Then we get to here. So now we've moved the object beyond. So you can sort of imagine you've got a mirror set up and you're sliding an object in towards it, and you're observing what happens with the image, and you'd have to have a screen set up here to see the image. We'll do this in class. We'll play around with some mirrors and actually, you know, see this phenomena in action. So we, you know, we start with our object outside of C, we get to C, now we're inside of C, but between C and F. So this one here we say is still real, it's still inverted, but now it's magnified. Now we have a magnified image. Okay, so it's bigger, right? Here, well, now this is a case which is a bit different. It's a special case, I guess, for a concave mirror. We actually have a virtual image here, right? So we can't form that image on a screen. In all these other cases we can, but not on this one. Okay, so this is a virtual image. It's upright. Okay, so notice there's a connection. If it's real, it's always inverted. If it's virtual, it's always upright. Okay, and this one's magnified. Okay, so one of our jobs in answering some of the problems in the textbook will be to actually draw these diagrams and sort of get an idea of, you know, draw a ray diagram to get an idea of where the image is, but then on top of that to use these formulas here to actually calculate, you know, the location of the image based on where the object is. Okay, there is one other case here which I'll just quickly cover. I'll call it case 5. It's a special case again, and this one is where you have the object placed at the focal point. And what we find here is that no image is formed. No image is formed. And that's because when you do your ray diagrams, so if you have some ray diagrams coming off, we find that the ray diagrams actually run parallel to each other, and so they never actually meet. Okay, so do a whole, yeah. So there's no image formed. Okay, and that's an important idea for later on. So we're saying if the object is at F, no image is formed. It's an important idea for later on because we can find the focal point of a mirror, of a concave mirror, by looking at, using a screen and forming an image for an object that's a long way away. What we could say here, hypothetically, we could say there is an image formed. It's formed at infinity, right? And so in practice, if you're looking through a telescope, you can say like an object, like a star or something, is really a long distance away, to the point where it's approximately an infinite distance away. So with something like that, we find that looking at the light from a star, through a telescope, then we see that the image that is formed will be formed at the focal point. Okay, so that's why it's a good application for telescopes. Okay, how are we going for time? All right, I'm going to finish up very shortly. I know I've mentioned here the mirror formula magnification. I think I'll come back and do a third lesson where we'll cover that. We'll look at some problems in the textbook where we have to apply those. So just a very quick last thing on convex mirrors. So convex mirrors, I said before, there's only one case. Okay, and here it is. So we have an object here. We have a focal point here. We have a center of curvature here. And we can do our ray diagrams again. So we have a parallel ray reflecting as if it came from the focus. And then we have a ray heading in as if it's going to go through the focus. Okay, and it reflects parallel. And so we project that back. We find the intersection of those 2 points. And that's where our image is. And so we say here, just one case, we say that the image, right? Sorry, so the image formed here will be virtual, upright, and reduced. So you can sort of compare that to the fourth case here with concave mirrors. We saw that we had a virtual upright image. So it's always the case that virtual images are upright, but with the concave mirror, we had a magnified image. Here we have a reduced image. Just to finish off, let's summarize a couple of things here. So what we need to talk, okay, so let's just quickly look. So if we have a line, say, through here, we can say this distance here is F, and then this distance to C is C. So we use lowercase f, lowercase c to refer to the distances, but we use the uppercase F and C to refer to the actual points. Okay, I'm back. Although this will just flow on as one video, I did have to stop and start again, so I'll have to edit those two together. Hopefully the segue is smooth. So last point I'm going to make here, really, just to end this off, is that when doing rays, when drawing the ray diagrams, so doing a ray diagram, the two important rays that we use, the ones that I would suggest, would be the one that the incoming parallel ray, that reflects through the focus, and the other one is the incoming ray passing through the focus and reflecting parallel to the principal axis, of course. That's easy to remember and apply for concave mirrors. Convex mirrors, it's really the same idea. It's just, we have to do the virtual rays behind the mirror. So, okay, that's it. Thank you.